Excuse me. Okay, if you have not already done so, please take out your journals. We're going to make a concept map that reviews forces of attraction that hold particles together in matter. You may want to turn your paper horizontal, but it does not matter whichever way you want to do it. Okay, up at the top, what we want to do is we want to put interparticle forces of attraction. Okay, so these are very similar to the forces of attraction that we talked about with the kinetic molecular theory. The concept map should still be up in the corner of the room. And it talks about with gases, they're very low forces of attraction, does not hold particles together. Solids, very high forces that do hold them together. Okay, the first kind that we're going to talk about of these is really a review from last semester, and that is going to be intramolecular forces. And it's a little bit leading to use the term molecules because we learned molecules as only being referring to covalent bonds. And we're going to use that as a little bit more generalized term. Now, intramolecular forces, we usually talk about that they are the forces that hold atoms together. Okay, so individual atoms, and also, so the holds atoms together, and then also these are really our traditional bonds that we learned about right before Christmas break. Okay, so our traditional bonds. And there are three types of traditional bonds or intramolecular forces that we learned about that hold atoms together. One of the first one being ionic. And if you remember, ionic is when electrons are transferred, and this occurs between a metal and a non-metal. Okay, you usually get that metal atom that's willing to give up one electron, turn into a cation. Usually the non-metal is willing to accept it and turn into an anion. Okay, the second type is a covalent bond. And a covalent intermolecular force or bond involves two nonmetals. This is where electrons are shared. Okay, that's why we can draw Lewis dot structures to show when pairs of electrons are shared. And then the third one is metallic. Okay, and if you remember, metallic bonding is going to occur between two metal atoms, and this is the sea of electrons. Okay, so ionic electrons are transferred, covalent electrons are shared, metallic, it is the sea of electrons. And typically when we are referring to these, ionic and covalent are usually referred to as the strongest, which is going to come into play when we talk about types of crystals and types of solids in the very last part of this unit. Okay, so intramolecular forces, again, is our traditional bond, and these hold, let's see here, atoms together. Okay, big major difference here is what are those things holding together. All right, so now if we come over on the other side, instead of intramolecular, we're going to have intermolecular. And you probably have more space on your paper, and that's probably a good thing. So I've got intermolecular forces. And if over here we held atoms together, these suckers are going to hold molecules together. I'm going to just abbreviate that there. Okay, so big major difference between the two sides of this concept map is that these hold atoms together, these hold molecules together, and that's really the big take-home message on this. And we should be able to describe all of them. Okay, now with intermolecular forces, we can split these up, and this is what we refer to as IMFs. When we abbreviate IMFs, you're going to hear me use that term a lot in this unit. This is the ones that we're talking about. And there's three types with these as well. Now, the two types can be broken into. Okay, the first type of intermolecular force we can consider being present in all molecules. All right, this is what we're going to refer to, or not what we're going to refer to, but what are called London dispersion. Okay, and the thing with London dispersion forces is these are kind of temporary charges that exist simply because electrons are on one side of a molecule, and that's it, okay? Now the other two are going to only be present in polar molecules. And if we haven't had a chance to talk about this, we will. We'll identify polar molecules or non-polar molecules based on their Lewis dot structures and the distribution of electrons. And so the two that are present in polar molecules are going to be one of two types. One is what we refer to as hydrogen bonding. And I really don't like the term hydrogen bonding because it's a little misleading. It's not really a typical type of bond that we had over here, but we still have to talk about it. And then the other one that's going to fall right in here is going to be dipole interactions. And really, they're just the fact that since any polar molecule has a positive end and a negative end, all the molecules are going to line up so that all of the positives and the negatives are opposite from each other. All right, now the last thing that we have to do is kind of rank these a little bit, because if we're looking at the two groups side by side, there's some separation. But first off, if we just look at the intermolecular forces, our hydrogen bonding, which is going to occur between hydrogen as well as either nitrogen, oxygen, and fluorine, this is going to be, let me scroll this down a little bit so you can see it. This is going to be the strongest type of intermolecular force. Okay, dipole-dipole is going to be, I'm just going to say middle strength, because if hydrogen bonding is the strongest, London dispersion is going to be the weakest. And then dipole-dipole is going to be right smack in the middle. Now, the one other thing, though, that we have to consider is that although hydrogen bonding is the strongest of the intermolecular forces, all three of the intermolecular forces are much weaker than the intramolecular forces. Okay, so all of these three are much weaker than are intramoleculars. Okay, and part of the reason that I'm summarizing this is that in 7D, when we talk about type of solids and types of crystals, most of their properties are going to be based on what type of forces are holding them together. And one of the easiest ways I know how to explain that is if you had something stronger like superglue holding two things together, it's going to take a lot more energy to rip those two things apart than, let's say, if you only had maybe Elmer's glue or a glue stick holding something together. And I'll keep referring back to that analogy, but we will continue to refer back to this concept map in terms of explaining the properties of solids and crystals. Okay, I hope that helps.